All right. So we are gonna right now we selected all the joints at the shear wall location, and I'm gonna do the same thing that I did for the columns. I'm gonna assign joint, restrain, and I'm gonna say hinge, and I'm gonna say okay. So right now we actually modeled the slab system along with its boundary conditions. What is the boundary conditions? We have columns at a specific location, we have shear walls. So our analysis results are going to be accurate just for the slab and the beam system. Like in the 2D, that's actually how we design buildings. We start with one slab. And like, let's say that you got to design a 10-story building. The first thing that we do, and all the stories are like the same, like each other, like they all have a typical story like this one. I take it alone and I do the 2D analysis. And then once I'm done with this, I will do the reactions at the columns and at the shear walls. So right now, you know, the column in this building, how much load they are gonna have. Like, let's say you find out that this column is gonna have 25 ton. So you are gonna design this column to resist the 25 ton just for this story, multiplied by 10 times because it's a 10-story building. And now, once you design this column, you have dimensions. So you can build a 3D model with the dimensions of the columns. Okay, so right now we are at the 2D analysis stage. And I can put my loads, like let's define load pattern, like the same way that we did before, dead load multiplied by 1. Here we are gonna keep the dead load multiplied by 1. Why? Because we wanted the software to calculate the dead load of this structure. What is the slab load and what is the column, everything, the beams. So I don't have to calculate them. But before in the frame and the beams, we don't have to do this because that's like a structure analysis practice. I'm giving you an example from the exam, and I don't want you to calculate your own weight. I'm giving you all the loads as a distributed loads and assigned loads, okay? So we are going to keep the dead load so that we let SAP 2000 calculate the own weight of the structure, and we are going to define another load case. It's called live loads. I'm going to make this 0 because I don't want the software to calculate the dead load and put it in the live load, okay? We calculate the dead load only one time. The own weight of the structure is in the dead load. Also, you can define another load case. It's called, let's see if it's here or not, dead roof live. No, it's not here. Okay, there's some, I believe in older SAP 2000, there was something it's called super dead or something, like we do it for the flooring, but we can't put it in the dead load. Is it there? Okay, more. Oh, super dead. Yeah, it's here. It was there actually before. Okay, so we have super dead. We can't do this, but I can keep it dead, and I put the covering, like the flooring and everything, in the dead load. Okay, so the dead load is gonna have the own weight and the flooring. Okay, it's the same thing. Okay, so but if you want, like for your analysis, if you wanted to find out what is the structural response due to dead load only without anything, so you have to make a separate load pattern for the dead load and separate load pattern for the flooring and covering. So actually we can do that. Let's say flooring, and we can make it as a super dead, and we can add and make sure that this is 0 and add a new load pattern, and then I'm gonna say okay. Really? And let's say define load pattern. Yeah, it's dead. So I'm gonna make this live, and I'm gonna edit, modify, and make it live load. Thank you. And so right now I define the load pattern, but this doesn't mean that the loads are assigned yet. I just to prepare the software that I'm gonna assign some load patterns. Let's assign them. So I'm gonna select all the slab system that I have, unless some parts of the slab has different load value. Sometimes when we design buildings, there's part of the slab has different load value, like the corridors, like if you have a library, if you have a storage. So every part of the slab can have different load value. But right now we are gonna assume that all the slab are having the same load value. Since we are done with the define, we are gonna go to the assign. I'm gonna go assign area loads, and I'm gonna go to uniform shell, and I'm gonna say that I'm not gonna assign anything to the dead, because in the dead, there's the on weight. The software is already calculating this. And I'm gonna say that I'm gonna assign flooring, and this flooring is gonna be, for example, 150 kilograms or 0.15 ton. And I'm gonna say apply. So right now, all the slab system has 0.15 ton per meter square on this slab. And I'm gonna go to the live load, and I'm gonna make the live load 200 kilograms or 0.2 ton. And I'm gonna say I have to select this first. It's not selected. So this is gonna be activated now. And I'm gonna say, okay. If you wanna make sure that all your loads are already assigned to the slab system, you can click on the slab, right click, and then it's gonna show you in the load tab what loads that it has. It has the live, it has the flooring, but definitely is not gonna show you the on weight, because the on weight is already embedded inside the dead load pattern. Okay, just when we assign the flooring, did we change it to super dead? Yeah. We change it? Okay. Are you guys sure? Right. It doesn't make any difference, but we want to show them separately. Okay, so right now we can define load combinations. I'm gonna go here to load combinations, and I'm gonna add new combinations. Let's open the standards and see what is load combinations that we have. I think it's in chapter 2. Load combinations. All right, here's the load combinations that we have. So you have to design for all these load combinations, like the dead load alone, 1.4 dead, and there's another combination, 1.2 dead plus 1.6 live plus 0.5 of the roof live load or the snow or the rain. So you have to include these. So it's like basically not one combination. You have to design for all of them and take the maximum, because sometimes dead load alone, like the building doesn't have any live load and has dead load. Sometimes it has the dead load, a live load, and other loads. So you have to define all these load combinations. But for the sake of simplicity, and we only do analysis, not design, let's pick 1.2 dead, 1.6 live.
Question. Why do we use 2.5 lightning or snow or rain? Like what's the idea of the using?
It's all about probability and statistics. All these numbers are coming from, like, there is no, like, you can design for an event that is really can happen. Like, it doesn't make sense that you design your building that the maximum earthquake is gonna happen with the maximum wind, with the maximum rain, with everything maximum happen at the same time. So the people who did this code, they take events, they take statistics and numbers and see what is the maximum that can happen together. So you increase the dead and you increase the live, but it doesn't make sense that all the dead load is gonna be there, but all the live load, like all the people and everything is gonna be in the building during the extreme rainfall or the extreme snow event. And the same thing when you design for earthquake, where you can win. We don't say that the maximum can happen for both of them at the same time. So we take some load combination between them. So I believe here like W is the win, so it's 1.2 dead plus 1 win plus the live plus 0.5. So you design for all these load combinations together. Okay. All right, so I'm gonna only use 1.2 dead plus 1.6 live. So I'm gonna get back to SAP 2000 and I'm gonna define a load combination. And let's say compo 1, the dead load is 1.2. I'm gonna add. And then flooring is a still dead load, so it's multiplied by 1.2. And live load is 1.6. So I'm gonna put this as 1.6. I'm gonna hit OK. So right now, if I go to modify, I will find all my load pattern is here. It's gonna multiply. And the software is gonna make a linear summation for all of them because there's different way that you can sum these load cases. Like you can do envelope to see, like it's gonna draw the bending moment for all of them, and it's gonna take the envelope, not taking everyone separately. Or there's actually some of the root squares of the loads. There's different way to add this combination, but we are gonna do direct summations, and I'm gonna say, okay. All right, so right now I can run the analysis, and I can say run now. So right now the analysis is done. And I can show whatever, I can show the reactions. So to show the reaction, show undeformed shape, you click on this one. That's gonna show you without any loads. Show deformed shape is the next one. This one, you can click on it. You can show the dead from the dead or from the combination that we developed. And also you can show contours, like you can show the contours in the Z direction. And I always love to show the contours because it shows you how is the deformation across the space of your slab look like. Like here, for example, I can see right now that the deformation in the direction of Z, look here. Last time it was less than, like, it was around 1 millimeter or something. Right now, after we did the load combination, instead, live flooring and everything, look, right now you have like 3 millimeters, like 3.3 millimeters. Okay, that's here. You wanna, and actually, this is where the maximum negative deflection is, like at these purple spots here. Okay. All right. I wanted to make this model 3D, but it's a small model. So we have time to make a much bigger building. So let's try to do this, and then we can create it to 3D if we have time. All right. So the next slab model that we have here. All right. So this is how the whole process starts. You are a structural engineer, and there's an architecture engineer. Had a building like this designed, I'm not sure, like office or maybe, actually that was like one of the buildings that I have in Egypt. So this was like, yeah, I can see they are all residential buildings. And there's an elevator here, like double elevator, and there's a staircase here. So basically, we have a flat slab. Well, you can do a solid slab, whatever you decide, depends on the span of the system that you have. But we are gonna do it as a flat slab system. And the architecture is gonna give you this plan and it's gonna ask you for the structural drawings. And to do the structural drawings, you have to do structural analysis. To do structural analysis, you need to build the structural system of this building. So I decided I'm gonna make this building, since it's gonna be 15-story or 10-story, I have to put some shear walls to resist the earthquake in the X direction and in the Y direction. Okay, so I have, if you can see, I start to put the columns and I start to put the shear walls, like this green one, the big one. I start to make a core, and this core is also a shear wall that has a wall here and 3 walls in this direction. Let me ask you, if an earthquake hit this building this way, like the earthquake direction is this way, which shear wall is gonna resist this earthquake? Which one? This one or this one? This one. Why? Because this one is very stiff in this direction, but this one, like here, this is my shear wall, this one, okay? If the earthquake is coming this way, that's very stiff to bend that way. But this way, it's very weak, can fall. Like when I put this book here, it's gonna fall this way, not gonna fall this way, right? Because this inertia is weak. Same thing, if the earthquake is hitting this way, all these shear wall, this one, this one, this one, is taking the earthquake in this way. That's why we do post direction shear wall so that we can resist the earthquake. All right, so let's model this. So I removed all the architecture stuff that I don't need. I'm only focused on the structural elements. And this is my structure. So I want to do this structure in SAP 2000. Let's look. I'm gonna do a grid system. Let's see what is the simplest grid system that I can use so I can draw this efficiently. I have the dimension 7, 5, 5, 5, 7. So 7, 3 5s, and 7. But I need a grid system here so I can draw the shear wall. So, and this shear wall are 3 meters. So I need to do 3, 3, and then 7. Same thing here, 0, 3, and 7. And in the y direction, I need to make sure that I make grid in the middle so I can draw this shear wall in the middle. And this is 1 meter, 3, and then 1. So I need to make sure after I make the next 5, I add 1 to be 16 and 3. Sorry, this is 7, 5 is gonna be 12, and this is 13, and with 3, 16, and then 17. Okay, so let's come here. SAP 2000, I'm gonna file. I'm gonna actually, you know what? I'm gonna save as this model. Why? Because I don't have to define new sections. I use the old section. Let's go to the area section. 20 centimeter. Well, let's file new model so that we don't mess with things. They've changed. All right, I'm gonna make sure that the units to meter, grids only. And the thing is, the grids are not uniform. So not uniform spacing. So what I'm gonna do, I'm gonna make the software create whatever grid system that we has. Like let's make 8 in X, 8 in Y, 1 in Z, and the spacing 6, and I'm gonna hit OK. Then I'm gonna edit this one. I'm gonna do a right click and I'm gonna edit the grid system. And I'm gonna say modify. And let's edit this numbers. So in X direction, if you guys remember, we have 0, 3, 7, 7 plus 5, 12, 12 plus 2.5, 14.5, and then it's gonna be 17, and this is gonna be 22, 22 plus 4, 26, and then 29. All right, so I'm gonna do, you guys remember? 3, 7, and then plus 5, 12, 14.5, 17, and then 22, 26. I'm gonna add another one, and this is gonna be 29. All right, let's get to the Y direction. The Y direction is 0, 3, 7, 12, 13, 16, 17, and then 22, 26, 29. All right, so you guys tell me 3, 7, 12, 17, Did I miss something? Let's see. All right, let's see what's gonna happen. All right, so. All right, I believe it's right. Let's see here. I think we missed something here. Look, here is not like here. It's kind of symmetric. So I'm gonna go to the Y direction and see what's gonna happen. Sometimes it doesn't enter the last one or mess up with the last one that you like. Here I have 32. This is should be 29. I'm gonna say. Well, it should modify right. Okay, let's see. Modify. 29. Should say okay. And okay, it should work. Yeah. All right. So right now I prepared the grid to draw the system. So let's see what the system has. The system has beams, has shear walls, has slab system, has some columns. The columns all are 50 by 50. And let's make this one 50 by 50 for the simplicity. We can make it differently, but it's gonna take some time. But let's make all the columns are 50-50. Okay, so the first thing that I'm gonna do, I'm gonna define the materials as we did before. Materials, I'm gonna use the default material, like this concrete, 4,000 pound per square inch. I'm gonna define the sections. So I'm gonna go to define sections. First, I'm gonna define the frame sections. I'm gonna add new property. I have all the system are concrete, so I'm gonna go to concrete rectangle, and I'm gonna make the columns first, C1, 50 by 50 centimeter. We're not gonna use them now, but we're gonna create them. So I'm gonna make them 0.5 by 0.5 and make sure that the material is concrete. I'm gonna say okay. And I'm gonna add another one for the beams. And I'm gonna define it as a beam 25 by 70 centimeter. And I'm gonna make this 0.7, 0.25. So I did the concrete, and I'm gonna do another one, a copy of this one, and I'm gonna name it F section 1. I'm gonna tell you what I'm gonna use this one. This one, we're not gonna use it. I'm just gonna, I mean, like, it's not gonna be real. I'm gonna use it for different purpose. Okay, and next one, I'm gonna define the slab section. So it's, which is an area section, because it's a slab. And I'm gonna add a new section. This section is gonna be slab 25 centimeter, and I have here 25, 25, the material 4,000 pound per square inch. Okay, and I'm gonna add a new section or a copy of this section for the wall system. I'm gonna say this is a wall set 30 centimeter, and I make sure that I change the thickness to 0.3, and the material is concrete, shell thin, and I'm gonna hit okay. So I defined all these sections that I'm gonna use in this structure. All right, so the next step is I start drawing the sections. So I'm gonna start by drawing the beams. So I have here, I make sure that the selection here is beam 25 by 70. I have beam all around this slab. It's called marginal beam. All right. The second thing, I also have a coupling beam here for the core system. I have this is a shear wall. The thing is, this is an elevator, right? You can make shear wall all around, but here there's the elevator door. So the only thing that you can do is a beam on top of this one, which is this beam. This beam is usually bigger than the marginal beam or stiffer. Okay, I'm gonna keep it the same dimension like the original beam. So I'm done with the beams. Let's do the walls. Okay, you will tell me for the walls we did hinges. I'm gonna draw a dummy beam at the walls location so I can identify where are these walls is when I draw the slab. And you are gonna find out later why did I do that. So I'm gonna make a frame and I'm gonna assign it to the frame section 1. And I know that I have a shear wall here and shear wall here. All right, I draw all the shear walls locations. So right now I know where are the shear walls. You'll tell me all the beams are yellow. No, but I draw them on a separate section. If I want to select the sections of the walls or where are the walls is, I can go to select and then select and then properties, frame section, and then I can select the section where are the walls at. I can delete them at any time. I can convert them to a shear wall at any time. So that's why I put them in a separate section. All right, so next I'm ready to draw the slab system. The slab system, look what I'm gonna do. I'm gonna draw rectangular area because this is rectangle. And I make sure that the slab system, the slab section is, we didn't call it slab 25. Okay, let me double check if the section is 25. That's why we usually name sections and put the characteristics of the section in their name. Let's call it 25. And then I'm gonna go back here, slab 25, and I'm gonna draw slab here for, not sure, did it draw it or not? Okay, here's our slab. Okay, so what is missing? Am I done? I draw the beams, I draw the walls, I draw the slab. What happens if I run the model now? There's no hinges. This is unstable system. And even if there's hinges, it is not divided yet. So basically the deflection in the middle is gonna be 0. Okay, so the first thing I need to put hinges, but to put hinges, I need to create joints but to create joints, I need to divide this slab verse so a joint can be created here, or I have to draw them one by one. So draw them one by one. I'm gonna have a lot of them. Maybe it's gonna take, I don't know, 5-10 minutes. But once we draw this, the joints are gonna be created, so it's gonna be easy to put the hinges. So I draw the slab. So what I'm gonna do, I'm gonna select this slab and divide it with the grid system. I'm gonna edit, divide area, and divide area again. And then I'm gonna see divide area based on points and at the intersection of visible straight grid lines. I'm gonna hit OK. So right now I can assign joints at the location of the column. I have a column here, here. You guys tell me if I missed any columns. All right, I believe I got all the columns location. Let's double check. I have columns all around here. I have 2 here. Okay. Get back. And then I'm gonna go assign, joint, restrain, and I'm gonna put hinge. Okay. All right. So what is next? Should I run the model or I missed something? But it's still like, are we satisfied with this big slab? It's still big, like this is like 5 by 5. It's a huge, so I need to divide them more. But you will tell me why we didn't divide them more at verse. The first thing, we need to divide them in a way that they can intersect with the columns. let's say, this is very important. Let's say that we at verse divided them 5 by 5. If we divided them at verse 5 by 5 randomly, you will end up with having like your hinges here and the mesh. Okay, the mesh is like this, the 0.5, and maybe the column in the middle is not connected to a joint. If the column is not connected to one of the mesh joints, the column is not going to feel that there's any slab here. As I told you, all the calculations and the boundary conditions and the analysis are done at the joints. So if this column somehow here in the middle or here, or maybe the column is in this position, but the slab top is like here, or the mesh is here, the column is not going to feel that there's a slab over there. You need to create a joint and define the mesh at the column's location. That's why we did this first. We divided this at the location of the grids where the columns at. So the columns right now feel that there's a slab here. And then we are going to divide them 5 by 5 or whatever mesh size that we would like it to be. So if you have, Zinni, if you have any like A4 paper, anyone? Sorry. Oh, this is I just need. Oh, there's one. Yeah. So that's actually a clear example. That's actually what I used to demonstrate. So the column needs to be at the joints of the mesh. That's the mesh. The meshes only have 4 joints. Okay, one here, one here, one here, and only feels load or deformation or anything at the joints. In between, there is nothing. It just makes some averaging in between. So if your column is here, the column is not feeling any load. The reaction is going to be 0. The deformation is going to be 0. Everything is going to be 0. But if your column is here, it's going to feel that there's a slab here. That's why we did this. There's a way actually to make this very easy. We usually do this on AutoCAD, where you can mesh and make everything on AutoCAD. Sometimes in AutoCAD, when we create the mesh, like the mesh is like this, right? And your column is here. What we're gonna do, we drag this point to here. And you'll tell me, but the mesh doesn't look good. It's fine. It doesn't have to be rectangle. You can have like I don't know, whatever shape it's gonna be. But we drag this mesh to the column. And if we have a beam and this mesh doesn't connect to the beam, we drag all the points to the beam so that the beam can feel the mesh. So that's how we do finite element analysis. All right. So we're done with this. I'm gonna select all these slab and divide them into small meshes, and I'm gonna edit area, divide area, and I'm gonna have here divide area into maximum size of 0.5 by 0.5. This doesn't mean that all the meshes are gonna be 0.5 by 0.5. I said just the maximum is 0.5 by 0.5. We are gonna have less than that. So I'm gonna say okay, and then it's gonna take a few seconds, and then we have our mesh. Look, if I zoom in, at any column, you'll find that the meshes are divided around the column. Interesting. That happens with SAP 2000 when it gets heavier, you will find some funny stuff. Okay, like let's say XY view, and then everything is supposed to be good, right? Yeah. Okay. So right now I'm done with the columns. I'm done with the slab, but I need to assign hinges at the location of the shear walls, right? Okay, so how can I do this? It's gonna be a little bit difficult. You have to zoom in and zoom out at each one, but let me try to make it a little bit easier. Even that I can actually, like I can zoom in here and I can select the joints here, and then I do it. What was that?
You can select the frame itself because it's dummy, and you select and divide it at the intersection of the slab.
You can do this, but if you select the frame, it's not gonna select the joint. It's gonna select the frame itself. You cannot assign. But if you divide it into small elements, you still have to select the joints. Like let's say, okay, I'm gonna select properties and frame section, and I'm gonna select frame section 1. So frame section 1 is gonna select the frame. We need to assign the joint not on a frame, on a joint, right? So we need to select the joints. The thing that I would do, just not for confusing me, I would, for example, go to the show display and remove the slab from the display, like not in the view. That's gonna make it a little bit different, but you still feel the joints, like here. If you click here, you will find joints, and in the selection, like here, you see, it's selected like 32 points. That's a way to do it. There's another way to do it. Like, let's show the slab again. Apply. I can, for example, select properties, slab section, or let's say frame sections. I'm gonna select all the frame sections that we have, this one and this one. Select. And I'm gonna do something here. It's called show selection only. All right, so the slab right now is not here. But let's find out if there's joints here or not. It's only selecting 2 points. The slab is not selected. I mean, like, I should select the joints in between, so that's not gonna work. But you can actually make these 2 joints. Let's make it that way. Let's put the joints here and make only the wall hinges at the start, at the end. But the right way to do it is like to put hinges all over the slab. But I'm gonna tell you something that is gonna make it a little bit closer to the right answer. All right. Okay, selected. Okay, and I have one here. So that made it easy. I'm gonna go assign, joint, restrain, and I'm gonna put hinges. All right, so what I did right now, I put hinges at the start, at the end, but it should be hinges all the way at this location. Why? Because there's a few at all these locations. Okay. The thing is, I can do this section and make the stiffness of this section, because what I'm doing right now, I'm not looking for reactions on the shear wall right now. I'm looking at designing this slab system in a good way. Like, I want to model this slab system. I want to find the reinforcement and design just the slab, not the columns, not the shear walls, just getting reaction. So to do this, I need this slab to feel that there's a shear wall here. If I run the analysis, the slab is going to feel that this is like a beam. And it's going to bend like a beam, and the reinforcement that you are going to calculate here is not going to be real. Okay, so to do this, you can increase the stiffness of this beam, like multiply it by 10 or 15 or by 20. That means I'm telling the slab that there's a very, very stiff element here. And this stiff element is a shear wall, but I didn't model it as a shear wall, but I put an equivalent beam that is very stiff. Like, the height of this beam is 3 meters. Like, the height of this beam, for example, is 0.7. If I multiply the inertia by 10, so that means we like replaced it with a beam section that is have a very high depth, big depth. Let's see the difference. I'm gonna show you right now. Okay, so I'm gonna keep it like this. Let's just show all again. Like, I'm gonna hit show all, so the slab is gonna show up, and I'm gonna select everything, especially the slab system, and I'm gonna assign the load. But before I assign the loads, I'm gonna define load patterns, same way like we did for the other slab system. Lauren. So we did. Gonna make 0, add live loads, and I'm gonna make it live. Okay, and I'm gonna go assign area loads uniform shell. The live load is 0.2. Let's apply this. I'm gonna select the slab again. I'm gonna do flooring. I'm gonna make it 1.15. I'm gonna say okay. All right, so right now I assigned all the loads and everything, and this slab is ready for the analysis. But before I run the analysis, I'm gonna show the undeformed. Oh, I stopped the recording. Share. Is it recording? Oh, stop. Okay. All right, so I'm gonna click F4. Or you click undeformed shape so we can have all this gone. The thing is, we have a void here because the elevator. So we need to delete the slab at this location. So what I'm gonna do, let me zoom here. I'm gonna select this area. I'm gonna delete these. I'm gonna delete these two. Okay. So right now we don't have slab at here, and we are ready to run the model. Okay, run now. Need to save this first. Oh, we need to define load combination. We can define load combination after the model run. That's totally fine. We don't have to unlock the model because you can do this because you don't do analysis. The analysis already done. That's post-processing. So it's gonna take a little bit of time more than the other one. Wow. Right. So let's show 3D. But before we do this, let's define load combination. And new. The dead load is gonna multiply by 1.2. Flooring the same thing. Live is gonna be multiplied by 1.6. Add. And I'm gonna show the deformed shape with contours due to this load combination. Combination 1. All right, so this is the deformed shape. And as we can see, this is the span that has the maximum deformed shape. And we are getting around 5 millimeter, like 0.5 centimeter here. Yeah, all right. I want you to notice something, that the lowest deformation that we have here is the blue one, right? The maximum is a big one, it's 0.52. The blue is almost 0, which is at the B range. There's a little bit of deformation. If we want to make it 0, you need to increase the stiffness of this beam. Like, let's see how much is the deformation over there. Like, let's stop the animation and go check on top of this, like 0.005, like even like 0.5 millimeter. Okay. If you can accept that, we can move on. But if we can't, you need to unlock the model like this. And actually, that's what I would do. And I'm gonna go to define section. And I'm gonna go to frame section, which is this section that I draw the wall with, and I'm gonna modify. And when you modify, there is something is called set properties, and I'm gonna increase all these properties and multiply them by 10, especially the bending moment and shear. Like the moment about x2 and 3, and the shear 1 and 2, 2 and 3, all of them, I'm gonna multiply them by 10, multiply the cross section, everything by 10. So that's gonna make a very, that means do you have a section 25 by 70 multiplied by 10, the inertia multiplied by 10, okay? Or you make hinges here. So, and you can delete this section. Both of them are the same thing. All right, so right now we are done with our model. Let's assume that we have done this, or we are accepting the 0.5 millimeter deformation. And you are going to show the rest of the analysis. So what we are interested in the slab system analysis versus the deformation, we need to make sure the deformation is meeting the deformation criteria for serviceability. As I told you, like the maximum deformation shouldn't exceed a specific limit based on the standards. And did I unlock the model? Oh, no. Okay, so let me, since I unlocked the model, I'm going to go define section. Frame section, and I'm gonna go to this one, modify, set modifiers. I'm gonna make this 10, 10, 10, okay, whatever, 11. And I'm gonna say, okay, I'm gonna rerun the model. So what I wanted to show you is the bending moment diagram. That's what we are interested in when we do analysis for slab system. Slab system, like beams, we're interested in the bending moment of the beam and the shear force of the beam. Bending moment, so I can get the reinforcement, and shear, so I can know how much stress should I put in the beam. Slab system, it's basically the bending moment in the X direction and in the Y direction. The bending moment in the X direction, so I put reinforcement in the X direction, and the bending moment in the Y direction, so I can put reinforcement in the Y direction. That's what we are interested in the slab system. Once the analysis is run, I go check the bending moment. There's a way that we can design based on the bending moment that we get from here and get the reinforcement for the slab system. But we are not doing design here. I'm just going to show you how to get the analysis result, how to get the bending moment on this entire slab. Once you get it, you can design it, find how much reinforcement, and do your structure analysis design procedures. And then you get the reactions of these columns, and design the columns outside, and also the reaction at the wall, and get a preliminary dimensions for these walls so that we can do this 3D modeling. All right. Okay, so let's check how much is the deflection now. All right. The deflection, U3, it got less, like it's 0.00. Let me zoom in. Like here, oh, it's like -0.5. Like it becomes way less. The more that you increase, the right answer is 0. Okay, but we are close to it. Okay, I'm gonna accept that. And I have my analysis is done, and then I want to convert this to 3D. So I'm gonna unlock this model. I'm gonna say okay, and I'm gonna make this XY. All right, to make this 3D, I'm gonna tell you how we can convert it 3D easily. Well, I need to get the slab system from the view, and I'm only gonna show the frame elements. So I'm gonna go select properties, frame section, and I'm gonna show all these frame section, select, and I'm gonna right click here. I'm gonna say show selection only. All right. Let's see if I have, I don't have the columns. Okay, that's fine. So what I'm gonna do, I'm gonna select all these, and the columns are not here. Okay, let me select the joints at the columns location I have here. Okay, so it sounds like in this, there's only frames. You can select joints, you can select shells. So I'm gonna select from here. I have columns here. Make sure I have how many joints selected. The counter is here. So that will tell us. I'm gonna select all the columns so that I can convert them to 3D. One here. All right, I believe I selected all the columns, right? Okay, and then I'm gonna go to edit. And in edit, you will find edit points, and then you will find, no, we are gonna go to extrude, and extrude points to frames. We are gonna convert points to frames. And here is gonna ask you what cross section of this frame is gonna be. I'm gonna say column 50 by 50, and the extrude direction is gonna be in the Z direction, and it's gonna be -3. Like take this point and pull it down to a frame in the negative direction, -3, and the number of extrusion is 1. Like I only need 1 column. Okay, so I'm gonna hit OK. And let's look at the 3D. So I'm gonna click 3D here. Oh, really? Did we put 2 numbers?
I think it was, 3 and 1.
3 and 1? Okay. All right, let's not select again and see if we can retrieve the previous selection. Hmm?
No, get the selection. Do a selection here.
Where? Oh yeah, get previous selection. It's down. All right, we got them, and then we are gonna hit edit, extrude. Let's see what we did wrong here. There was 3 at Y. Don't know how. Okay, let's 0, 0, -3, and we're gonna say okay. So right now it's right. So we are done with the column. So what I'm gonna do next, I'm gonna also select the previous selection, and then I'm gonna assign joint, restrain, and remove the restraint that it has. Okay. So there's no hinges on the top, okay? All right. And the next thing is the walls. So what I'm gonna do, I'm gonna select the frame section that I draw the wall with, and actually that was F section 1. I'm gonna select this one, and I'm gonna do something is called edit extrude lines to area. And this section is gonna be walls 30 centimeter, -3, 1, and delete the source object. You can delete it if you want, or you can keep it right now. Maybe at the end, I can delete it. Okay, so I'm gonna hit OK. So right now I have the shear walls, all right? Okay, so right now I have the columns, I have the shear walls, but what I want to do right now, I'm gonna go to XY. Right now, we're not gonna have hinges at the floor system. The floor system right now is gonna be supported by columns, and the columns have the hinges because it's supported by the foundation. Okay. All right. We have hinges at first because we didn't have columns. We don't know what is the columns dimension is, but right now we got reaction, we got everything, design the columns, draw the shear walls, and then book hinges at down. Okay, the thing is, how can I put hinges? First, let's remove this hinges first. Assign joint restrain, and then say okay. All right. I'm gonna draw. The thing is, I wanna see the grid system down. So I'm gonna edit the grid system, and I'm gonna modify, and I'm gonna add a grid system at -3. So I can see the joints in the -3. So I have 0. I'm gonna add another one, Z, at -3, and I'm gonna hit OK. All right. And then this is all right. I have here XY plane at Z equals 0. So what I'm gonna do, I need this recording thing to go up. All right. Gonna go up. Can you see these two arrows? This one is gonna go down in XZ. This is Z0. Okay, let's make sure it draw. I think, yeah, it's not here yet. So let's put -3. I don't know why I have to do it twice. Say okay, modify it. Okay, let's try -3 and give it Z2. And say okay. All right, so if we go down, right now it's supposed to go to Z -3. All right, here we go. We are at Z -3. If you make a selection here, it will select all the joints at the end points of the frames. And right now I can assign joint restrain, and I can put hinges, fix it, depends on the foundation type. And I will be done for now. And next time on Thursday, we are gonna finish this model. Okay, so right now this model still has a lot of things to do. I need to define the shells, and I need to connect it with the slab system. And then we assign the load and show how the 3D is gonna look like. Okay, so we're gonna stop now, and next time we're gonna continue this one. Yeah.
So what besides the size of the shear wall, it's the compressive force and not the lateral force.
Well, we are not. What do you mean? Like we are just modeling the geometry. We didn't get to the forces.
Yeah, but when we design a shear wall, what is the governing factor for deciding the size? Is it the lateral forces?
It's close. Well, we do preliminary section like the way that we did it now, and then based on the vertical forces. This we get the dimension, and then the reinforcement. Once you do the seismic analysis and wind analysis, you will get bending moment in the X, bending moment in the Y, and design it as a biaxial member. So then you will find out that this shear wall is gonna have lots of reinforcement here, lots of reinforcement at the end, at the start, and maybe also some reinforcement distributed. Depends, because the shear wall has getting the reactions like this. So it has tension here, compression here. So you have lots of reinforcement here and lots of reinforcement here. And the reinforcement is getting less as soon as you get to the neutral axis. So it depends on the moment. So basically it's the moment in this direction. So, right? But we are not designing, we're just like do the analysis and get the forces. Okay, right? Okay, see you guys next time. And stay safe. Next time, there's no in-person class for the people who came late. We're gonna do it online. I'm gonna send an announcement with details, right?
So,